Okay, so those who have joined the class of finite element can give their attendance in the chat box. I repeat, those who have joined the class for finite element method can give their attendance in the chat box. Just give me a minute so that I can present my screen. Can anyone please respond whether my slides are visible or not?
Yes, yes, visible.
Okay, thank you. So, before starting today's class, let me give you a brief recap of what we have did in the last class. If you remember, in the last class, we have taken this problem. That is, yes, we have taken this problem and we have seen that by direct stiffness method, how we can get the nodal displacement as well as the stresses present in the given problem. And also we have discussed about that if in a one dimensional bar element, if that element is having some uniform cross sectional area A, if the element is made up of a material whose modulus of elasticity is E, and if the length of the material is L, then the stiffness matrix is given by stiffness matrix of that particular element is given by k minus k k. We can take this k out from the matrix. If you take this k out, the resulting matrix becomes k in matrix form 1 minus 1 minus 1 1. And if you remember, in the very first module we have derived that the value of k is given by the relationship E into A by L. So in place of K, I will replace that K by E into A by L, 1 minus 1 minus 1 1. So this is the final resulting, that is, this is the final resulting stiffness matrix for a particular element. And we if we want to find out, or if we want to evaluate the stress present in the element, how we can find out? We know the Hooke's law, that according to Hooke's law, within the elastic limit, stress is directly proportional to strain. That is, stress is equal to modulus of elasticity into strain. So the stress for a particular element is given by E into this strain in FEM is given by B matrix into displacement vector transpose of displacement vector matrix. What is this B matrix? This also I have told in the last class. This B matrix is nothing but the strain displacement matrix. How this matrix is coming, that we will discuss in the fourth module. Fine. For the time being, in order to solve the problem, just remember this relation. And the strain displacement matrix is given by, it is nothing but two 1 cross 2 matrix. You can see this is one row and two column. So you can write it as, that is 1 upon LE matrix, 1 cross 2 matrix minus 1 1. What is this LE? LE is nothing but the length of the element. So if I multiply this 1 upon LE term inside the matrix, the resulting strain displacement matrix become, that is 1 cross 2 matrix, that is minus 1 by LE and 1 by LE. So the resulting stress present in any element in matrix form is given by modulus of elasticity E into B. This B matrix is nothing but this matrix minus 1 upon LE for the element 1 upon LE for the element. This is nothing but 1 cross 2 matrix. You can see that there is 1 row and 2 column into UE transpose. What is UE transpose? This is nothing but nodal displacement vector elemental matrix. For example, if this is my element, in this element, if this is node 1, this is node 2. If I assume that displacement of node 1 is U1, displacement of node 2 is U2, then this element displacement vector matrix for this particular element will be given by U1 U2. That means 1 cross 2 matrix transpose of this 1 cross 2 matrix. If you take the transpose, you know that in transpose, row becomes column and column becomes row. So I can write this matrix as U1 U2 for this particular element. Then it will be 2 cross 1 matrix, that is 2 row and 1 column. Finally, this UE, this matrix becomes for this particular element U1 and U2. For any other element, say that is this is element number 2 and this element number 2 is connected between node 2 and node 3, then definitely this displacement value will be U2, this displacement value will be U3. Then this matrix will become, this will become U2 and this value will become U3. Is it clear to all of you? Any doubt so far? Hello? Any doubt so far?
No,
Yes,
sir.
sir,
No, sir.
clear, sir.
Okay, fine.
No.
So, by the help of these things, by the help of these conditions, we will try to solve one problem. This problem is little bit different from the problem that we have solved in the previous class, because in today's problem we will be requiring these informations. Fine. Okay. So now let us solve this problem. Some person is joining. Who is joining? Okay, Udesh is joining. Fine. Okay. So let us read the problem. The problem is a brass bar of length 3 meter. That means the entire length of the bar is 3 meters. Starting from A till point D, the entire bar is made up of brass whose length is 3 meter. It is subjected to loads as shown in the figure. That means the brass bar is divided into three. This is nothing but a composite problem. The entire brass bar is divided into three composite bar, namely AB, BC and CD. And you can see in the diagram that for brass bar AB at point B, load acting is 100 kilonewton, tensile in nature. For bar BC at point C, load acting is 40 kilonewton, compressive in nature. For bar CD at point D, load acting is 20 kilonewton, which is also compressive in nature. Okay. Next, what is given to you? The segment AB is of length 0.5 meter. AB is having length 0.5 meter and diameter is 50 mm. If dia is given to you, that means it is very much clear that the cross section of this bar is circle. Okay. So what is given to me? That is this length. This length is how much? It is 0.5 meter. And the diameter, that means this part is how much? This part is 50 mm. Okay. Next, the length BC is 1 meter. That means this particular length BC is how much? It is 1 meter. And diameter is 20 mm. This particular diameter is how much? 20 mm. Length of CD is 1.5 meter. That means this length CD is how much? It is 1.5 meter. And diameter is how much? This diameter is 30 mm. Fine. E is 100 gigapascal. The entire bar is made up of one material, that is brass, whose modulus of elasticity given is 100 gigapascal. What you need to find out? You need to compute the stresses in the three segments of the bar using FEM. That means what will be the stress in the portion AB, what will be the stress in the portion BC, and what will be the stress in the portion CD. You have to compute by FEM. That means I have to use which method? Direct stiffness method to compute the stresses present in the given bars. Is the problem clear to all of you? Any doubt in the problem so far? Hello.
सर एक बार फिर से रिपीट कर दीजिए.
फिर से रिपीट करूं. You have came late. In the problem, what is given to you? A brass bar is given to you. Entire length of the bar is 3 meter. This brass bar is nothing but a composite bar made up of three sections. The first section is AB, second section is BC, third section is CD. In the section AB of the bar at point B, a tensile load is acting, that is 100 kilonewton. In the section BC of the bar at point C, a compressive load is acting, which is 40 kilonewton. And in the section CD of the bar at point D, a compressive load is acting minus 20 kilonewton. By FE and length of the bar AB is 0.5 meter. BC is 1 meter, CD is 1.5 meter. Diameter of the cross section of bar AB is 50 mm, BC is 20 mm, CD is 30 mm. What you need to find out? By FEM, you need to compute the stresses in the three segments of the bar. That means what will be the stress in bar AB, in bar BC, in bar CD by FEM. That means I have to use which method? Direct stiffness method. Now is the
Yes,
question
sir.
clear to you?
Yes, yes, sir. Clear, clear, sir.
Okay. So since we have to use the concept of FEM, and we know that in FEM what we do? In FEM we divide the entire geometry into some finite number of elements. So can you please tell me in this problem how many elements I will divide the entire problem? How many elements we will divide the entire problem? Hello. Please tell me how many elements we will divide the entire problem. It is very much clear from the diagram that the entire problem has to be divided into three elements. This is my element number 1. This is my element number 2. This is my element number 3. If there are three elements, how many nodes will be present? Number of element plus 1, that is here the number of element is 3, so total node will be 4. That means this is node number 1, this will be my node number 2, this is my node number 3, and this is my node number 4. That means node element 1 is connected between node 1 and node 2. Element 2 is connected between node 2 and node 3. Element 3 is connected between node 3 and node 4. And at nodal point 2, force acting is plus 100 kilonewton. At nodal point 3, force acting is minus 40 kilonewton. At nodal point 4, force acting is minus 20 kilonewton. And if I want to see the boundary condition, so I can see that at nodal point 1, displacement of the bar AB at nodal point 1 will be 0. Why 0? Because it is fixed end. If I assume that node 1 is having displacement U1, node 2 is having displacement U2, node 3 is having displacement U3, and node 4 is having displacement U4, linear displacement. Then from the problem, it is very much clear that U1 is equal to 0. Is it clear to all of you? Any doubts so far? Any doubts so far? Okay. If no one is responding, then I will assume that there is no doubt. Let me move forward. Next is what? Next, we will define element attribute table. What is element attribute table? Element attribute table is nothing but the entire property of each and every element. So the first column is your element. Second column, nodes. That means first element is connected between which and which node. Third column is the length of the
One to four.
element.
First element.
Fourth column is the area of the element. Fifth column is the property of the element, that is nothing but the modulus of elasticity E. And what is the last column? Last column is nothing
Yes.
but the stiffness of the element, because in FEM we normally assume each and every element to be a spring, so it will have some stiffness value. Since in this problem three elements are present, so there will be three stiffness. That means for first element stiffness value is k1, for second element stiffness value is k2, for third element stiffness value is k3. Is it clear to all of you?
Yes, sir.
Okay, so we are having element number one. I can see very clearly that element one is connected between node one and node two. So nodal connectivity is 1 to 2. Element number two, it is connected between node 2 and node 3. See, element 2 is connected between node 2 and node 3. Element number 3 is connected between node 3 and node 4. You can check element nodal connectivity for element 3 is node 3 to node 4. So first and second column we have completed. Let us come to the third column. That means we have to input the values of length for each element. It is given in the problem that AB is having a length of 0.5 meter, BC is having a length of 1 meter, and CD is having a length of 1.5 meter. If you add all these three values, you will get the total length of the entire problem as 3 meter. So AB is 0.5 meter, BC second element is 1 meter in length, and third element is 1.5 meter in length. We have completed the third column of the table. Is there any doubt is there till the third column of the table?
No, sir. Clear, sir.
Okay. Next is we have to compute the area of each and every element. Why? Because if you see in the problem, it is given that each and every element is having a cross section of circle whose diameter values are given to you. So why I need to calculate area? Because I know the formula for stiffness as E into A by L. If you won't calculate A, you will not be able to compute the value of stiffness for each and every element. So let us calculate the area of each element. So since the cross section is circle, we know that area is given by pi by 4, that is area is given by pi by 4 into d square. Area is given by pi by 4 into d square. For element number 1, diameter will be d1. For element number 2, diameter will be d2. For element number 3, diameter is d3. So let us calculate the area of element number 1. It is how much? Pi by 4 into d1 square. And in the problem, dia for element 1 is given. You can check that segment AB is of length 0.5 meter and dia 50 mm. So dia for element number 1, that is D1, is how much? 50 mm. So pi by 4 into, I am converting it into meter, so 50 into 10 to the power minus 3 whole square. If you solve this expression, you will get the area of the element to be 1.9634 into 10 to the power minus 3 meter square. In similar fashion, you have to calculate the area of element 2 and element 3. What will be the area of element 2? It will be pi by 4 into d2 square, and for element number 3 it will be pi by 4 into d3 square. From the question I have to compute the value of d2 and d3. So it is given that length of the BC means element number 2 is 1 meter and dia is 20. That means d2 is 20 for element number 2, and for element number 3, which is CD, dia is 30 mm. So if you use the formula of area, you can get the area of second and third element. So for second element, area is coming out to be 3.141 into 10 to the power minus 4 millimeter square, and for the third element, area is coming out to be 7.068 into 10 to the power minus 4 meter square. So far we have completed 4 columns, first 4 columns. Any doubt in those 4 columns?
No, sir. Clear. Clear.
Okay, the next column is I have to input the material property. Since the entire problem is made up of one material, that is brass, whose modulus of elasticity is given to you, and the value of E will be same for each and every element, and that is nothing but 100 gigapascal, that is 100 into 10 to the power 9 Newton per meter square. So this is your fifth column. What is the last column? Last column is computation of stiffness for each and every element. Just now I have told you that stiffness is given by the expression E into A by L. Stiffness is given by E into A by L, and when you write it in matrix, this is the matrix equation, but in general in mathematical form, stiffness is given by E into A by L. That means for element number 1, stiffness will be E into A1 by L1. For element number 2, it will be E into A2 by L2. For element number 3, it will be E into A3 by L3. So
H3 divided by H2.
if I compute the stiffness of element number 1, it will be E into A1 by L1. A1 E is given, that is 100 into 10 to the power 9 into A1. Already we have calculated for the first element 1.963 into 10 to the power minus 3 divided by L1. L1 means length of the first element. If you see, it is given in the problem that segment AB is of length 0.5 meter. So this L1 is 0.5 meter, and if you solve this expression, you will get the value of stiffness for the first element, which is coming out to be 39.26 into 10 to the power 7 Newton per meter. In the similar manner, you will compute the stiffness for second element as well as for third element. For second element, the stiffness becomes, that is, for this element, the stiffness becomes E into A2 by L2. E is same. A2 will be nothing but this particular value by L2. What will be L2? It is given. L2 is nothing, means length of the element 2. Element 2 is BC. Its length is 1 meter. That means this value of L will be 1 meter. And if you compute this expression, you will get the value of the stiffness of the second element. In similar manner, just compute the stiffness of the third element, which will come out to be 4.71 into 10 to the power 7 Newton per meter. So we have completed the overall element attribute table. Any doubt in this table?
No, sir. Clear, sir.
No, sir. No doubt.
Okay, fine. Next step is what? We know. Next step is we have to compute the local stiffness matrix for each and every element. Since there are 3 elements present in the problem, so there will be in altogether 3 local stiffness matrix, and after that what we will do, after that we will assemble these three local stiffness matrix to get the global stiffness matrix, and then we will write down the governing algebraic equation for the problem, which is nothing but the restoring force, that is K into U is equal to F, in which K is what? K is your global stiffness matrix. What is U? U is your global load displacement vector. What is F? F is your global U is your global displacement vector matrix, and F is your global load vector matrix. So before going to that particular thing, first let us find out the local stiffness matrix for each and every element. So for element number 1, if I want to compute the stiffness matrix, I know that stiffness matrix is given by which expression? That is for element number 1, Ke means for element number 1. So K1 is equal to E into A. Which A? A1. For element number 1, area is A1 divided by L. Which L? For the first element,
A1
what is
length.
the length? L1. Then in matrix form, 1 minus 1 minus 1 1. So let us write it down. And I know what will be the order of the stiffness matrix. Order of the stiffness matrix will be equal to the number of node present in the element. If I am talking about the first element, you can see first element is comprising of two nodes, that is node 1 and node 2. So the size of the stiffness matrix will be a 2 cross 2 matrix. Size of the stiffness matrix will be 2 cross 2 matrix, and I know that this represents the first node, second row represents second node, first row represents first node. Similarly, first column represent first node, second column represent second node, and so on. Fine. So it is how much? It is 1 EA 1 by L1, 1 minus 1 minus 1 1. So E into A1 by L1 already we have computed for the first element, which is 39.26 into 10 to the power 7. Matrix 1 minus 1 minus 1 1. Now if I keep 10 to the power minus 7 out of the matrix, and if I bring 39.26 inside the matrix, then what I need to do? I have to multiply each element of the matrix with this 39.26. Then the resulting stiffness matrix becomes K1 is equal to 10 to the power 7, 39.26. That is 39.26 into 1 is 39.26. 39.26 into minus 1 is minus 39.26. Similarly, this will be minus 39.26, because 39.26 into minus 1 is minus 39.26, and 39.26 into 1 is 39.26. So this is equation number A. Equation number A is nothing but the local stiffness matrix for element number 1. Is it clear to all of you? Any doubt so far?
Clear, sir.
Okay. Similarly, for element number 2 and element number 3, again we have to find out the element stiffness matrix. For element number 2, stiffness matrix is K2. It is equal to E into A. Which A? Second area of the second element, that is A2 divided by L. Which L? Length of the second element, that is L2. Again, now you have to decide what will be the order of the stiffness matrix. Again, I know that order of the stiffness matrix will be equal to the number of node present in the element. I can see very clearly that in element number 2, two nodes are present, that is node 2 and node 3. So the size of the stiffness matrix for the second element will be again a 2 cross 2 matrix. It will be again 2 cross 2 matrix, and I know that the first row represent node 2, the second row represent node 3. Similarly, first column represent node 2, last column represent node 3. So E into A2 by L2 for the second element is how much? 3.14 into 10 to the power 7. Again, I can take I have to multiply this 3.14 inside the bracket. Just multiply it and keep 10 to the power minus 7 outside the matrix. Then K2 is equal to 10 to the power 7, 3.14 minus 3.14 minus 3.14, 3.14, which is second equation, that is equation number B. That is the final resulting local stiffness matrix for element number 2. Is it clear to all of you till equation number B? Any doubt?
Clear, sir.
Similarly, for element number 3, the stiffness matrix becomes K3 is equal to E into A3 by L3. Then stiffness matrix 1 minus 1 minus 1 1. Again, I have to decide what will be the order of the stiffness matrix. For that, I have to see the element. So I can see that element 3 is comprised of two nodes, node 3 and node 4. So the size of the elemental stiffness matrix will be 2 cross 2 size, and the first row will represent third node, fourth row will represent fourth row will represent, yes, that is so the first row will represent node 3, second row will represent node 4. Similarly, first column will represent node 3 and second column will represent node 4. Now I know that for third element, stiffness is given by E into A3 by L3. Now A3 and L3 I know, that is A3 is nothing but this value 4.71 into 10 to the power 7, and what is L3? For L3, I need to see the question. It is given, see, length of CD is 1.5 meters. So L3 becomes 1.5 meter. And if you solve this expression, you will get this particular value. That is 4.71 into 10 to the power 7. Again, I can multiply 4.71 with each of the element of the matrix. So just keeping 10 to the power minus 7 out of the matrix, multiply 4.71. Then the final resulting stiffness matrix becomes 10 to the power 7 2 cross 2 matrix, in which the first row is 4.71 minus 4.71 and the second row is minus 4.71 and 4.71, which is equation number C. Is it clear to all of you?
Yes, sir.
Okay.
Yes,
Next
sir,
step
clear.
is what? Next step is I have to assemble all these local stiffness matrix. Assembling means A plus B plus C. While adding, if something is coming in negative, definitely you have to minus it. And if everything is coming in positive value, not an issue. Fine. So just assemble A, B, and C, and I know the assembled one, that is a global stiffness matrix, is nothing but an assembled matrix. So what will be the size of that assembled matrix? How I will understand the size? I will understand if I look at the problem. I can see that in this problem, total 3 elements are present and total 4 nodes are present. So the size of the global stiffness matrix will be equivalent to the total number of nodes present in the problem. So the size of the global stiffness matrix for this problem will be a 4 cross 4 matrix. Is it clear to all of you?
Yes, sir, clear.
Other people, please respond whether it is clear or not. Hello. Okay. So see, this is my 4 cross 4 global stiffness matrix, in which this is my first row, second row, third row, fourth row. First column, second column, third column, fourth column. And the thing which I have encircled in with pen outside the matrix, this represent node. That means first row is nothing but first node, second row is nothing but second node, First column is nothing but first node, second column is nothing but second node, and so on. Okay, so just assemble. How I will assemble? So if I see this value, that means I need to write this particular value. This value will be one first row and first column. So from A, B and C equation, we will find out what is the value of first row and first column. So from A, the first row and first column is 39.26. From B, there is no first row and first column. From C, there is no first row and first column. So ultimately, the value becomes 39.26. Is it clear to you?
Yes, sir.
Yes, sir.
Similarly,
Clear.
I want to write now this particular value. This particular value is what? First row and second column. So from the elemental stiffnesses matrix, let us find out what is the value of first row and second column. So from equation number A, first row and second column is how much? Minus 39.26. From equation number B, I won't take because there is no first row. Second column is there, but first row is not there. Similarly, from equation number C also I will not take because here third and fourth row and column is present. So my final answer of this particular value is what? First row and second column. It is first one. It is nothing but minus 39.26. Is it clear? First row and second column minus 39.26.
Yes, sir. Clear. Clear.
Similarly, if I find out the first row and third column, that is this value. This is what? First row and third column. What will be the value? Let us check equation number A. There is first row, but third column is not there. No use. If I see equation number B, third column is there. Third column is there, but first row is not there. I won't use equation B. For sorry, this is what? This is for element number one. This is for element number one. Since yes, so first row and third column in equation number three, there is no first row and third column. That means this first row and this third column, this particular value is not available in any of the equation A, B, and C. That means I have to put it as zero. Is it clear to all of you?
Yes, sir.
Fine.
Yes, sir.
Similarly, in this manner, you have to complete this entire global stiffness matrix table. If say this particular value, second row and fourth column, that means this particular value, if it is present in any of the equation, then only I will write. If it is not present, I will write it as zero. Now let us substitute this particular value, that is second row and second column from equation A, B and C. From A, I can see that second row and second column is 39.26. Then from equation number B, again second row and second column is there, that is 3.14. But from third element, neither second row nor second column is there. So the final assembled value, that is this particular value, this is what? Second row and second column is how much? It is 39.26 plus 3.14. 39.26 plus 3.14. Did you got my point?
Yes, sir.
Yes, sir.
Likewise, you have to complete the remaining coefficients present in this global stiffness matrix. So after adding all these things, that is 39.26 plus 3.14, 3.14 plus 4.71, final resulting matrix is which one? This is your final resulting matrix. That is, this is your final resulting global stiffness matrix. After adding these two things, is it clear to all of you?
Yes, sir.
Fine. Now I know
Yes, sir.
that the governing algebraic equation for the problem is nothing but The governing algebraic equation for the problem is nothing but K
into U
stiffness
into
matrix
F.
K into U. U is what? U is your nodal global nodal displacement vector is equal to F matrix. What is F matrix? F matrix is global force vector matrix. Fine. Since I know that in this problem total three elements are there and in altogether four nodes are there, so the global displacement vector for this problem will be what? Will be U of element transpose. U of element will be for first element, that is for first element U1 U2, for second element U2 U3, for third element U3 U4. So U1 U2 U3 U4 transpose. If you transpose it, this particular row becomes column. So it is nothing but 4 cross 1 matrix, and it is U1 U2 U3 U4. Similarly, if I talk about assembled load vector, since four nodes are present, let us assume that each node is subjected to some axial force. Each node is subjected to some axial force. So assume that force acting at node 1 is how much? F1. F2 already given 100 kilonewton. F3 will be minus 40 kilonewton, tensile in nature. F4 will be again minus 20 kilonewton. F4 will be again minus 20 kilonewton. Is it clear to all of you?
Yes, sir.
Fine. So let us write all these things in matrix form. Let us write all these things in matrix form. So this is your global stiffness matrix, 4 by 4 matrix into that is column matrix, column, that is assembled nodal displacement vector matrix U1 U2 U3 U4 equal to assembled load vector matrix F1 F2 F3 F4. Now if we know that the first row represent node 1, second row node 2, third row node 3, and the fourth row is node 4. Similarly, first column node 1, second column node 2, third column node 3, fourth column node 4. Is it clear?
Yes, sir.
Fine. So next, what is this process? If you want to solve this algebraic equation, first you have to see whether any boundary condition is present or not. If you see this problem, in this problem, at the extreme left end, it is fixed. That means node 1 is fixed. If node 1 is fixed, displacement at node 1 is 0. That means U1 is 0. So after applying boundary condition, we came to know that this U1 value is nothing but equal to 0. Is it clear?
Yes, sir.
And from the problem, the fourth boundary condition is at 2, the force acting is plus 100 kilonewton. So F2 is plus 100 kilonewton. At node 3, force acting is minus 40 kilonewton. That means F3 is your minus 40 kilonewton. And at node 4, force acting is how much? Minus 20 kilonewton. So value of F4 is minus 20 kilonewton. Since nothing has
Yes, sir.
been given about force F1, so I will assume that F1 is 0. I will assume that F1 is 0. So the final resulting matrix equation becomes this particular matrix into, see, U1 is 0, but remaining displacement of node 2, 3 and 4 will be there. So it is U2, U3, U4 equal to nodal force vector. Since nothing is no information is given about nodal point 1, what is the force? I will take it as 0. For nodal point 2, force is 100. For nodal point 3, force is minus 40. And for nodal point 4, force is minus 20. That is compressive in nature. And since these forces are in kilonewton, so if you want to convert in Newton, it will be into 10 to the power 3. So I have taken it out from the matrix into 10 to the power 3. Is it clear so far till this particular expression?
Yes, sir. Yeah.
Yes, yes, sir.
Okay, now if you want to solve this expression, then which method will I use? If I want to solve this matrix equation, which method will I use? I have told you in the previous class that I have to use Gauss elimination method. I need to use which method? I need to use Gauss elimination method. And Gauss elimination method tells us that since this U1 is 0 and this F1 is 0, that means RHS is 0. If I see first row, in first row RHS is 0 and in first column this u1 is 0, then according to Gauss elimination method I can remove this first row as well as this first column, because u1 is 0 and f1 is 0, output is 0. If output is 0, I don't need this equation. So Gauss elimination method says that you have to remove that equation. So if I remove, that means I am removing the row 1 and column 1. Then the resulting matrix becomes this particular matrix, 3 by 3 matrix containing column 2, column 3, column 4, row 2, row 3, row 4. Corresponding to row 2, at nodal point 2, displacement is u2. Corresponding to row 3, at nodal point 3, displacement is u3. Corresponding to row 4, at nodal point 4, displacement is u4. And corresponding force values are also given in the problem, which is equal to, again it will be a 3 cross 1 matrix, that is 100 minus 40 minus 20 outside bracket 10 to the power 3, in order to convert from kilonewton to Newton. Is it clear to all of you, this Gauss elimination method? Any doubt?
No, sir, clear.
Fine. So you are having three equations. You are having, that means if you multiply this row with this column, it will be equal to 100 into 10 to the power 3. You will get one equation in terms of u2, u3 and u4. If you multiply this particular row with this particular column, you will get RHS equal to this particular value. Similarly, if you will multiply this particular row with this particular column, you will get the third equation, which is equal to this minus 20 into 10 to the power 3. So you are having three equation and three unknown, that is u2, u3 and u4. With this you can get the value of u2, u3 and u4, and it is coming out to be, after solving, I haven't solved, you please solve it. It will be displacement of node 2 is 0.102 mm, displacement of node 3 is minus 1.810 mm, and displacement of node 4 is 2.230 mm. Is it clear to all of you? Is it clear to all of you?
Yes, sir.
Fine. That means, so please add one line in the question that you need to compute the stresses as well as compute the nodal displacement also. Please add one line in this question. In this question only you need to compute the stresses, but you cannot compute stresses if you don't compute nodal displacement. So just add one line in the question that also you need to compute nodal displacement. So this is my nodal displacement, u2, u3 and u4, and obviously u1 is 0. Fine. So I will take 5 more minutes. After that, this problem will be over, and then you can leave the meeting. I will take 5 more minutes to get the value of this stresses present in the element AB, BC, and CD. How I can find it out? For that, I have to use the stress equation. I know what is my stress equation. That is, stress present in any element is equal to modulus of elasticity E into strain displacement matrix, which is nothing but this particular matrix, into your nodal, that is assembled nodal displacement vector transpose. That means this assembled nodal displacement vector transpose will be what? It will be nothing but u transpose, that is u of element. Sometime in some books you can find it is written to be q also, so that's why here I have written u oblique q. That's why I have written u oblique q. In some book you can see that q is also written. So q element or u is nothing but it will be, since four nodes are present, so it will be u1, u2, u3, u4 transpose. So at present it is 1 cross 4 matrix. 1 cross 4 matrix. In transpose, I have to convert this row into column. It will become u1, u2, u3, u4. Fine, which is nothing but this particular matrix. Here I have given the values. u1 is 0, u2 already we have found out, that is 0.102 mm, u3 is minus 1.810 mm, and u4 is 2.230 mm. Is it clear to all of you? Any doubt in this? This nodal displacement vector matrix?
No, sir.
Okay, thank you. So now we can find out the value of stress present in each element. So if I talk about element number 1, I know this is my equation of finding out the stress in FEM, that is sigma of element. Which element? First element. So sigma 1 is equal to E into, this is what? This is my strain displacement matrix, minus 1 upon LE into 1 upon LE. LE is what? LE is the length of element number 1. Since in the given problem it is given that length of first element is how much? 0.5 meter. So minus 1 upon 0.5, 1 upon 0.5 into your nodal, assembled nodal displacement matrix transpose. But in this matrix, which values will be coming? Since I am talking about element number 1, you can see that element number 1 consists of node 1 and node 2. So this global, so this nodal displacement vector will consist of only node 1 and node 2. Displacement of node 1 and node 2, that means u1 u2 transpose, that is u1 u2. Fine. So E we can substitute 100 into 10 to the power 9 matrix, minus 1 upon 0.5, 1 upon 0.5. Then in column matrix, U1 is 0, U2 is 0.102. If you want to convert it into meter, into 10 to the power minus 3. Now this is what? If you see, this matrix is 1 cross 2 matrix. That means 1 row and 2 column. And this particular matrix is 2 cross 1 matrix. That is 2 row and 1 column. That means the multiplication of these two matrix will be what? Will be a 1 cross 1 matrix. That means I have to multiply row with column, this row with this column, that will be this particular value. That means minus 1 by 0.5 into 0 is 0, plus 1 upon 0.5 into 0.102 will be some value. If you solve it, the stress present in element number 1 will come out to be 20.4 megapascal. Is it clear how I have calculated how I have calculated the stress in the first element?
Yes, sir. Clear.
Okay, fine. Similarly, you can calculate the stress in the second element. For second element also I am showing you. You can do it for the third element by yourself. So for second
Sigma 2.
element, sigma E. E means for second element, so it will be sigma 2 is equal to E into strain displacement matrix minus 1 upon LE into minus 1 upon LE, 1 upon LE. Now this LE will be what? This LE is nothing but the length of the second element, and in the problem it is given that the length of the second element is 1 meter. So minus 1 by 1, 1 upon 1 into, this is what? This is the nodal displacement vector matrix for second element, and I can see that for second element only two nodes are present, that is node 2 and node 3. So this nodal displacement vector matrix will consist of node 2 and node 3. So u2 at node 2 displacement is u2, at node 3 displacement is u3 transpose. If you do the transpose, it will become u2 and u3. u2 already you have calculated, u3 already you have calculated. Just solve this matrix equation, you will get the value of the stress present in the second element, which is minus 191.2 megapascal. And what does this minus sign indicates? This minus sign indicates that the stress present in the second element is compressive in nature, and the plus sign in the first element indicates that stress present in the first element is tensile in nature. In the similar fashion, you can calculate the stress present in the third element. Okay, any doubts so far?
No, sir. Clear, sir.
Okay, so with this, I end the today's lecture over here. So tomorrow, 3 to 4 p.m., I will not be able to take the class. So that class will be taken by our respected HOD sir. So in order to compensate tomorrow's class, tomorrow only from evening 7 to 8 p.m., I will take that class. Okay, and I will share the link by 6:30 p.m. Okay. Okay, so if anyone is left to give the attendance, you may give, or else you can leave the meeting. Thank you.